Okay, for today's lecture, we're going to look at a little bit more complicated situation, a little bit more involved, and I replaced the tip on my pen, so it should work really well today. So we have two charges, Q1 and Q2, and we're interested in what's the electric field at some point in space. These are a little different. We did them something very similar with forces, but when you do it with electric field, you just pick some point. There's not necessarily a charge. There's nothing necessarily there. It's just a point that we're interested in. You might say, well, why on earth would I care about this? Imagine if you lived near power lines, pole lines. Well, you might want to know, okay, I'm this many yards or 100 yards away from the pole line. Is there any electric field? Am I affected by all these electronic devices that I use every day? I'm just looking around myself. I have my computer and I have my tablet and I have a cordless phone not too far from me. And they're all giving out electric fields and radio waves and things like that. So we might be interested in that. The first thing we need to do is to draw our field lines. This is a positive charge, so it points up. Here, because the other charge is negative, and I know that's not real straight, that's okay. It points down and to the right, towards the negative charge. And you say, uh-oh, we've got angles here. The positive charge is really easy to work with. The negative charge, we're going to have to do some geometry and some trig. To find our electric field, we're going to just use the E equals KQ over R squared, just the standard formula. So let's see where we go with this. We need to find the distance to the negative charge. So if you look, that's a 0.4 is one leg of the triangle. Maybe that's A. This is B. To find C, we just use Pythagorean theorem, just like in geometry. So C squared is A squared plus B squared, right here. And then C squared, we have to substitute our 0.4, and we get 0.5. Now to get the angle in here, we'll use our good old friend tangent. Opposite over adjacent. And we get 53.1 degrees. Oops, so let me not go too fast here. So you can see all I did right now, this is just geometry. There's not really any physics involved here. This is just, I have to figure out the triangle. Now E is KQ over R squared, like we just said. So what we're going to need to do is figure out the first electric field. That was the electric field for that positive charge, and it points straight up. We don't need to do any trig. We don't need to do any geometry. So E1 is 3.94 times 10 to the 5th newtons per coulomb, and it'll be straight up. So we could say that's in the J direction. Oops, I got that weird line again. Maybe it wasn't the tip on the pen. Now E2 is a little longer direction. It's the 0.500, I think it was meters, yeah. Half a meter, 50 centimeters. We'll just calculate that. But the problem with E2 is it points downward at an angle. We already know the angle. We already calculated that at 53 degrees, 53.1. So we're going to have to calculate the X and the Y component for it. Because it's pointing down and to the right. Now it is pointing to the right, just like in an XY axis. It is pointing towards the positive x-axis. But it's pointing downward, so EY will be negative. So here's another picture of it where we're trying to break it down into the EY and EX. You don't necessarily have to take notes on these, but you can. But you always have the video to refer back to. Oops, I guess I did it all at once here. So to get the X component, now remember our angle was right in here, 53 degrees. So I used cosine because that's adjacent. So it's E2 times the cosine of that. and that'll be to the right. That's our I component. Now to get the y, that's opposite where the angle is. So opposite over hypotenuse, that's the sine function. The hypotenuse is the 1.8 times 10 to the 5th newtons per coulomb. 10 to the 5th newtons per coulomb. So that ends up being negative. That's our j component. I guess I should put them with the little hat, although I don't put them with the little hat. PowerPoint doesn't make that real easy for us. So now we've got things in I and j notation. And remember, E1 only had a y component. There was no angle to worry about. So now I'm going to set it up. So E1 is nothing in the I direction, but pointing straight up. E2 was pointing over this way, so it has a positive x component and a negative y component. And I just added downward. 0 plus this is 1.80 times 10 to the 5th. 3.94 times 10 to the 5th minus 1.44. Now those subtract. Right, so that's kind of weird. Yeah, E1 was going up, and E2's y component was going down, so they will subtract. They will cancel each other a little bit. Now that's our resultant in unit vector notation. Oops, I think I forgot the j there. We'll add it in. Unit vector notation. So what we see here is, and remember we always read left to right. We do x first and then y first. We go over 1.08 times 10 to the 5th. We go up 2.49 times 10 to the 5th. So to get the magnitude of the resultant electric field, the overall electric field, we use Pythagorean theorem. And we get it right there. 2.72 times 10 to the 5th. Then we're going to use tangent. The tangent function to get the theta. So the tangent of theta is y over x. And that just works out to some number. Oh, let's see what it works out to. 2.49 divided by 1.08, and they're both times 10 to the 5th. So it's 2.31. So to get the theta, we take the inverse tangent of 2.31. And let's double check my math here. And yeah, 66.6 degrees. You could say north of east if you want. Not a bad idea to give it a vector, notation there. So after seeing this video, I'm probably just going to give you 1 or 2 problems because I know these take a while, and then we'll do another day of this, and then we're going to have a quiz at the end of the unit. So thanks for watching.